Welcome to this video in which I want to tell you a little bit about our paper on trial-wise decoding from fMRI using searchlights when trial-wise correlations are present. And this paper was published in Imaging Neuroscience in 2025. So as you probably know, fMRI data analysis is widely based on the general linear model, or GLM in short, which decomposes a single voxel Bode signal Y into experimental conditions and potential confounds, the design matrix X, weighted by some regression coefficients beta plus noise or error terms, which are also in the data and cannot be captured by our model. In multivariate pattern analysis, this condition-based design matrix is often exchanged for a trial-wise design matrix in which each trial has its own regressor, its own HRF regressor. This is called the least squares all approach and gives us trial-wise response estimates. The disadvantage of this is that when trials are spaced closely in time, the HRF regressors are overlapping, which induces serial correlations into the trial-wise parameter estimates. For this reason, another approach was proposed, the least squares separate or LSS approach, which uses a separate model for each trial, having one regressor for that particular trial and another regressor for all other trials. And although this makes estimates more robust, it obviously needs more computational resources. More recently, GLM single has been proposed as another alternative. GLM single uses fractional ridge regression along with other advances to come up with robust single trial estimates. And in a neuroimage paper from 2020, we have proposed inverse transformed encoding models, or ITEM in short. And here the focus is not so much on robust single trial estimates, but specifying a single trial model which accounts for the covariance of the trial-wise parameter estimates. So here's how it works. The trial-wise design matrix XT can be used to compute trial-wise response amplitudes gamma hat using least squares. And the condition-based design matrix can be related to the trial-wise design matrix via a transformation matrix T, which basically specifies which trial belongs to which experimental conditions. One can then show that the trial-wise parameter estimates, gamma hat, are following a new trial-wise model, which uses T as the design matrix and whose covariance matrix is the uncorrelation matrix U, which derives itself from the trial-wise design matrix and the scan-by-scan covariance matrix V. This transformed encoding model can then be extended to multivariate fMRI signals by combining multiple voxels, and it can be inverted to then finally predict experimental condition information from trial and voxel-wise response estimates. So in the present work, we extend this to trial-wise decoding, which means that we have spherical searchlights moving through the brain, and from each searchlight we are extracting the trial and voxel-wise responses. We are specifying the transformed encoding model using the transformation matrix T and the uncorrelation matrix U, and then the transformed encoding model is inverted to come up with predictions for the experimental design information, T hat. In simulations in which we were varying the distribution of intertrial intervals as well as the signal-to-noise ratio, we found that especially in low variance and low interval situations, ITEM consistently outperforms all the other approaches in terms of decoding accuracy. This also holds true when we were extending our simulations to a different number of trials, different number of voxels per searchlight, and different proportion of informative voxels per searchlight. So for empirical validation, we apply this to a visual reconstruction dataset. In this experiment, subjects were viewing such a circular stimulus, which featured flickering checkerboard stimulation and was composed out of 48 sectors that could be organized into 4 rings and 12 segments. So we then used Searchlight-based item to reconstruct the visual contrast or illumination intensity in each of the 48 sectors, which gave us 48 accuracy maps for each subject. We then performed a repeated measures ANOVA with eccentricity and angular direction as within subject factors. And in this way, we were able to recover several well-known properties of the visual system, such as the contralateral processing in visual perception, the representation of top, bottom, and medial versus lateral parts of the visual cortex, the representation of eccentricity along a posterior-anterior axis, and the representation of angular direction along a perpendicular dorsal-ventral axis. So this is it. If you want to know more, if you want to see more analysis, feel free to check out the paper. There's also an interesting appendix on parametric modulators in SPM. And with that, thank you and goodbye.